Good morning to everyone. Thank you for giving me the opportunity to give this talk. Today, I'm gonna talk to you about how we can use the Eagle simulations in order to obtain insights about the evolution of gas kinematics across cosmic time. So first of all, the first question, of course, is why gas kinematics evolve at all across cosmic time? And a short and also a big answer that we can say is just like the consequence of the interplay between many different physical processes. And I'm going to enumerate 4 of them that I'm using and I am analyzing in my project. So to start, we can mention, for example, the effect of feedback, either from massive stars or from AGN, which both of them inject energy into the ISM to the gas. Then the gas can transform this thermal energy into kinetic energy and then change the kinematic. Also, it can be found that there can occur the formation of massive clamps in the disk of galaxies that happen because of the creation of local instabilities, which can create transport mechanism in the disk, and also create local instabilities in the disk and in the gravitational field, and then changing the kinematics as well. Of course, these 2 processes are regulated by the effect of inflows and outflows that can both change the efficiency of, they can change the number of star formation rates and also the occurrence of these gravitational instabilities. And of course, as well, we know that the galaxies live in dark matter halos, which can have many satellites, and then which can interact with our central galaxy and can, of course, can create mergers and then changing all the distribution of the gas and then changing the kinematics. So all of these processes can change the kinematics, can impact the kinematics, but in particular, all of them can change the velocity dispersion of the gas. And an important thing here is that we can use the velocity dispersion because it encodes information about all of these processes in the galaxies. So if we can understand how the velocity dispersion relate to all of these processes, we can also get insights about galaxy evolution. So the velocity dispersion has been widely studied. Here I'm showing recent data compilation from mostly surveys that observe the galaxies, observe the emission length from ionized gas in the galaxies. And the first result here is that you can see that velocity dispersion increased with redshift. And the main question is trying to understand which of these physical processes is creating this increase in the velocity dispersion with redshift. So before moving into the physics, I'm gonna point out how the gas velocity dispersion is measured. So in observations, in general, is mostly done using the IFU surveys from where we can obtain the velocity field of the galaxies, and also the gas velocity dispersion profile. And in the case of the simulations, there are many techniques, but one of them is using either spherical or cylindrical apertures and use all the gas particles within that aperture and use that to obtain a mass-weighted quantity, velocity dispersion. But also, as in observations, we can obtain a profile for the velocity dispersion. In this case, I'm showing the vertical velocity dispersion, so the dispersion along the rotation axis of the galaxies as a function of the radius. And in general, what is done in order to obtain a single value for the velocity dispersion of the galaxies is using a specific aperture. It can be the half mass radius of the galaxies or another radius that where the velocity dispersion doesn't change too much. So using this method, we can obtain all our measurements for all our Eagle galaxies, and that is what we did, which is shown here, where I'm showing a comparison between the results from Eagle with respect to the observations. And you can see here that the agreement is very well with respect to observations. So as I mentioned before, we want to understand what are the physical drivers of this evolution. And our approach in this project is trying to understand first what is driving the scatter in the, for a single redshift, what is driving the scatter in the velocity dispersion, and then trying to understand how the physical processes change with time, and then we can get insights about what are the main drivers of the gas kinematics. So from now on, in the rest of my talk, I'm going to show results that correspond to redshift 0.1 and analyze the different physical drivers. So here I'm showing all the galaxies that have a well-defined gas velocity dispersion measuring the half mass radius of the galaxies. And here you can see we can get more than 5,000 galaxies. And as a first order, you can see that the velocity dispersion depends with the stellar mass, so basically in the gravitational potential of the galaxies. And so as I was mentioned before, we also, when we look at this plot, we also observe a very big scatter in this relation. So there are many different, our aim is trying to understand what is driving this scatter in this relation. And from now on, I'm going to show you some qualitative results comparing two distributions. In this case, the red galaxies and the blue galaxies, which correspond to the extremes of the distribution of the velocity dispersion. So first of all, we look at the evolution, or we look at how different are the specific star formation rate of this sample, which you can see in this particular plot. So this is the specific star formation rate as a function of stellar mass. And the first thing that you can see is that the galaxies that have higher velocity dispersion also tend to have higher specific star formation rates. Although for masses above 10 to the 10.5, you start seeing this drop in the specific star formation rate, mainly because of the effect of AGN feedback that start to suppress the star formation. And also when we analyze the size mass relation, which is shown here in the top panel, you can see that galaxies that have higher velocity dispersion also tend to be smaller with respect to the galaxies that have low velocity dispersion. So when you normalize the star formation rate with respect to the size, you can see that these lines start to segregate a bit more. So in principle, this would mean that the stellar feedback seems to be more efficient in hitting the gas particles and changing the kinematics when the galaxy is small. We also look at the effect of inflows and outflows. So this is in the y-axis is in the left-hand side panel is the accretion rate as a function of stellar mass. In the right-hand side, the outflow rate as a function of stellar mass. And again, you can see here that overall, all the mass regime, you can see that galaxies that have higher velocity dispersion also display higher inflows and outflows. So these galaxies tend to have a constant outflow, constant flows of gas across all their history. Also, as a proxy for looking at the environment, the effect of environment, we are here I'm showing in the y-axis the halo formation time, and as a proxy, we are using the time when the galaxies, when the host halos of these galaxies have formed or have accreted 50% of their mass, and plotting that against the stellar mass of each galaxy. And here you can see, so the points that are lower in this plot tend to are more likely to have had major mergers across their history. And in general, you can see here that the galaxies that have higher velocity dispersion, the host halos of these galaxies tend to have formed later in time in comparison with the ones that have low velocity dispersion. So this is basically saying that these galaxies, or the dispersion, is being driven by the effect of mergers as well, or other interactions with other substructures. Also, I want to mention briefly the effect of the gravitational instabilities. I must mention, though, that we can do this analysis in Eagle only for very well-resolved galaxies, so very massive ones with in the order of a couple of thousands gas particles and stellar particles in order to make this analysis. So here on all the top panels, I'm showing the gas surface density of Eagle galaxies in phase-on projections. And in the bottom panels, you can see the 2D maps of the Q instability parameter, the Thomson stability parameter, which is usually used to quantify the effect of regions of instability in the 2D maps of the galaxies. And in the left-hand side, the first two examples, you can see that the galaxies that have high velocity dispersion also tend to have very massive and big clamps in their 2D maps. And in the case of the low velocity dispersion galaxies, they tend to have smaller clamps and very smaller and less massive clamps in general.
2 minutes.
Thank you. So just to summarize, we found that in general, the galaxies that have higher velocity dispersion tend to be smaller, and this could be the effect of stellar feedback. And also notice that this is only valid for low mass galaxies. So in principle, stellar feedback seems to be very efficient on changing the kinematic in low mass galaxies. Also, we found that across all the mass range, the velocity dispersion seems to be driven by the inflow and outflow rates as well, while also the host halos of the galaxies with high velocity dispersion tend to be formed at later times than the ones that have low velocity dispersion. And also we found, especially for high mass galaxies, we found that these galaxies with high velocity dispersion tend to display large and massive clamps. So it seems to be the effect of gravitational instabilities. Thank you for listening, and happy to take any question.
So thank you very much. So is there any question for Esteban? So I'm correct, I don't see any question at the moment. Then let me ask you one question. So you briefly mentioned about the environmental effect related to merger. So I'm just curious if most of the galaxies are located in low density environment, or some galaxies are in kind of cluster or group environment.
Yeah, well, in the case of low mass galaxies, most of them tend to be located in low density environments. Of course, there is a dependence here in environment as well as a function of the stellar mass. But yes, it depends on the environment, of course, but in general, we see that the galaxies that even in all the environments, you can see that the galaxies that have lower velocity dispersion tend to have formed earlier in time. So the main takeaway message from here is that the halos that have had more mergers in recent times, no matter the environment, they display more, they are more turbulent.